Hello and welcome back to our guided project on predicting mobile phone prices, and we're trying to use Ensemble methods in this guided project. So going into the pre-processing section, from the EDA that we did above, we noticed that there are some exponential distributions, and so we can see FC was one of the ones that I identified. We can see it's not exactly a perfect exponential, it's kind of a weak exponential distribution, but you can see it goes down and off to the right. This is not the best for modeling, as these outliers, not outliers, but this tail over here will pull the average towards that. And so as your model is building coefficients, it will essentially pull it towards this tail, even though that might not be the best representative coefficient for the entire data set. So to prevent that from happening, what we want to do, we can take the log of our variable. So what we'll do is we'll go df fc, and I like to change the name just in case we decide we don't want to use it as we're experimenting. Kind of setting up an experiment is the way that I look at this. We want to see if this works, so I like to assign this to a different column and not just overwrite the original. So what we can do next is we'll go np.log, and we're going to put this in the series. So we'll give this the data frame and then just the feature we want to use, so just FC. I'm plussing this by 1.1 just to, what happens if you have a lot of zero values, it won't work well. So this is going to move, essentially shift the column a little bit to the right so there are no zero values to allow us to take the log of this column. And so if we run this right here, and we can see the FC log right here. Although not a perfect, it's not a normal distribution, but a nice kind of neater, not so much of a tail. Still, it's not perfect, but it is a much better distribution now, as it's semi-normal-ish. It's more normal than it was before, and the average would be a good representation or a better representation of this data set, which means it would work well for modeling. Okay, so, and we can see here, printed out, just did a value count to make sure there were no zeros or null values in this. So another one that we looked at was the pixel height, so px height. And so if we run that, you can see the distribution. Again, it's not a perfect normal or exponential, it's a very weak exponential distribution. So let's see if we can make this a little bit better though for modeling. So we'll go df, and then as a string, we'll go px, as a string, we'll go px underscore height underscore log, and then closing bracket is equal to np dot log, and we're going to take the log of this series. So df, and then we'll go height, or sorry, px underscore height, and closing brackets. Okay, and then we want to make sure we have the outside parentheses as well. So we're going to take the log of this. We're adding one again to prevent, because there are a lot of zero values in this. So just to allow our log to look a little bit better. So what we'll do then is we're going to look at the log, and we can just look at the distribution. I looked at the count to make sure there were no zero values, to make sure that, to confirm that this +1 helped us do the log transformation. You can see here we still have 2000, and we have our distribution here. We do have some zero values, but if we take the log of a zero value, it becomes a null value. So it's okay that there's zero. We just don't want null values. And so if we're taking the log of a zero, we get a null, and that doesn't work well for modeling. So that's where that +1 comes in. So if we look at the height now, the log distribution, we can see a little bit more normal distribution. And so we're moving things a little bit better. Here we're going to take, we also identified the SC underscore W distribution. And so what we can do is, you can see here again, a very weak exponential distribution, but we can make this a little bit better. So let's do the same thing. So let's go, we're taking this to the SCW. So let's go S as a string, SC underscore W underscore log, closing parentheses, or closing brackets, equals to np dot log, and then the series of, just the series of this. So df dot sc underscore w, and then we're going to add 1 to this as well, just like 1.1. I just found that 1.1 sometimes works a little bit better than just 1, but it's kind of exploring and seeing exactly which works the best, and this is why we want to inspect it right after. Oh, and I forgot a bracket there. Oh, I have one too many brackets right here is the problem, and so this bracket I don't need, and so let's run this again. And we can see now we're looking at the printout of this, and we can see a much better distribution. This is a uniform, but this is a much better representation for our data set. So now that we have so many numeric features, what we can do, a really powerful technique is looking at binning the features, essentially turning a continuous variable into categories. We're going to break it up into 4 pieces, and then we'll have essentially a category of those pieces, and then we'll be able to go from there. And this will help our model find non-linear patterns and should give us a better score. Okay, so what we'll first do is we'll decide which of the continuous features we would like to bin. So features underscore bin is equal to the features that we'd like to bin. To show you what I did right here, so df feet, or sorry, let's just look at one of these. So let's look at battery power. So let's look at this. So we can see here, and I'm going to run the cell up above as well before I forget. We can see here we get the quantiles of this. So we can see where they are. NP linspace is going to basically give quantile a linear space between 0 and 1, and we're going to break it into five points, which will give us 4 different bins. And we can see here this is the points. So I'm going to put this into the function below. So what we're going to do is 4 feet in feature bin. So we're going to go for battery power, for clock speed, for int memory, for m depth, and we're going to put it in here. We're using an f string, so f, and then in the curly brackets we'll put the feature name, and we're going to go underscore bin, and this is to make a separate column, a separate feature for each of these bin categories, just in case we want to go back and use the originals. So we'll go here pd dot cut, and we'll go df, and then what we want to do is bins equals to, and we also want to make sure here what we do is df feet, so we're going to cut the feature, so for each feature in our data frame, so df feet, bins feet, we're going to take the quantile of from 0 to 1, so it's going to take an equal spaced 0 to 1, and we're going to give it the labels A, B, C, D, because we're going to get 4 of them. So we're 5 bins, we have to 5 values to outside the outer border, the outside edge of each bin, but we're only going to have 4 bins. So 5 outside edges relates to 4 bins. And so we're going to do that. And so run that through a loop. And we're good. And then we're going to print it out as a loop. So we'll go 4 feet in bin feature. We're going to do the name as well. And just to print it out and take a look at it. And this is perfect. This is exactly what we were hoping for. So here we have equally in equal quantities, although not each one will be the same, but we have them in quantities between or into 4 bins. So now A, B, C, D, and A would be the lowest value, B would be the second lowest, C, D, and D would be the biggest. So now we have category features instead of a continuous variable, and we can use this in our modeling. So going into the next section, so looking at this, we're going to look at getting dummies. So I just print out here the df.columns to get a list of our column names, and what we want to do is all the features that we've identified as category features and we would like to use them in our model, we would need to one-hot encode those. Here I also have, I can just copy and paste this to put in our bins, and so we'll create a list of features underscore cat, and then the features that we would like to put into our one-hot encoding. So what we'll do is we'll go df equals to pd dot get dummies, and what we want to do is give it the data frame and then the columns that we want to use. So we'll go columns features cat, and so this is going to then, so let's make sure we run the one up above first. So run this, and then let's run this. And so we can see here, we didn't have that many different columns here, but now if we run this again, we can see that we have a shape of 72 features in our data set. This is actually quite large in our feature. So we're building a big data set, and that's good for our modeling.